A compiler exists to translate human-readable source code into the exact physical instructions required by a machine. To get there, the code moves through three primary stages. First, source code analysis, then the generation of an intermediate representation, finally, the translation into target machine code. It is this final stage, target code generation, that presents a mechanical problem. Early code generation algorithms operate with extreme tunnel vision. They take each intermediate instruction and translate it into hardware instructions in strict isolation, with no awareness of the surrounding context. Because this process relies on rigid one-to-one translation templates, the resulting output is naive code. It is mathematically correct, but highly inefficient. Look at this translation. A single line of intermediate code expands into a bloated sequence of 6 target assembly instructions. It's packed with redundant memory operations, convoluted jump pathways, and dead code that will waste processing cycles. The compiler has to clean up this localized bloat, but running a global data flow analysis across the entire program at this stage is far too computationally expensive. The solution is a hyper-localized final cleanup pass known as Peephole Optimization. Rather than analyzing the whole program, the compiler employs a small sliding window. This peephole scans just 2 to 4 target instructions at a time, searching for recognizable patterns of inefficiency that it can replace with shorter, faster sequences. This localized pattern matching provides a rapid method to tighten up the final physical instructions right before the program executes. Before this sliding window can begin replacing instructions, the compiler establishes strict operational boundaries to ensure those replacements are safe. It does this by dividing the control flow graph into basic blocks. Here, we see a distinct block of assembly code. The defining rule is strict linear execution. The program enters at the first instruction and exits at the last, with no branching in between. This rigid constraint is mandatory because the peephole window relies on physical adjacency. It assumes that if instruction B follows instruction A, they execute sequentially. If an instruction inside the window has a label, that guarantee vanishes. The program could have jumped there from anywhere. When a random jump occurs, the sliding window cannot safely assume the instruction immediately preceding the label was ever executed. Without the strict boundaries of a basic block, applying local optimizations could corrupt the logical flow of the program. With the boundaries locked, the first pass begins. The peephole window drops onto the first 2 lines of the basic block. The window immediately scans for its first heuristic target, redundant memory accesses. Here, the first instruction loads a variable into a register, and the second instruction immediately stores it back. This accomplishes nothing. Because these instructions are inside the basic block, the window deletes the redundant store instruction. The window then shifts down to a mathematically poor translation. This triggers algebraic simplification. Multiplying by 1 or adding 0 are artifacts of generalized code generation. The window deletes the instruction. Next, the optimizer looks for strength reduction, replacing mathematically correct but hardware-intensive operations with cheaper equivalents. Calculating an exponent requires many CPU cycles. Simple multiplication achieves the exact same result much faster. The window swaps them. A similar reduction occurs with division. Dividing by a power of 2 is replaced with a bit shift operation, which is cheaper at the hardware level. These physical and algebraic reductions leave the program's logic untouched while reducing the hardware cycles required for execution. The optimizer now advances to a new phase, turning its attention to the boundaries between blocks, specifically flow of control instructions like jumps. In this sequence, a jump command targets label L1, but L1 immediately issues another jump to label L2. Intermediate code generation frequently chains multiple jumps together, acting like a game of logical telephony that bounces the processor around memory. The window applies a heuristic to resolve the final destination. The compiler traces the pathway, identifies L2 as the true destination, and updates the original instruction to point there directly. This process also applies to conditional jumps that point to unconditional jumps, bypassing the middleman and pointing the condition directly at the final target. Hardware thrives on straight-line control flow. Untangling these jumps prevents the CPU's instruction pipeline from stalling out while it tries to predict where the code is heading next. Now the window evaluates this debug block to apply its final category of heuristics, unreachable or dead code. In its current state, the machine has to jump over another jump just to proceed. The window applies conditional inversion. By flipping the logic to check if debug is not equal to 1, the middle jump is deleted, compressing the code. We can push this further through constant propagation. If a previous optimization proved the debug variable is 0, the inverted condition is mathematically guaranteed to be true. This leaves the next block of code physically situated directly after an unconditional jump. Because the program will always jump to L2, the debug print statements become stranded. They can never be reached, so the window deletes them. Deleting dead code brings previously separated instructions physically closer together. We've deleted redundant stores, simplified algebra, redirected jumps, and erased dead code. To be effective, the optimizer must perform multiple passes over the code. When we removed a jump to a jump earlier, it left a label stranded with nothing pointing to it. If we delete that stranded label, a load instruction and a store instruction that used to be separated by dead code suddenly fall into the same two-instruction peephole window. This is the optimization cascade. Every localized replacement has the potential to create an opportunity for a new improvement. Because of this cascade, the compiler iteratively runs the sliding window over the target code again and again. This loop only terminates when the window completes a full pass without making a single change, achieving a stable state. By combining a simple sliding window with a compounding chain reaction of heuristic rules, Peephole optimization forms the critical bridge between abstract theory and physical execution.